In this video, I will show you two calculations, one from the area of physics, another one from chemistry. The first calculation from physics will involve forces and leverage. Here is the situation. You're trying to tighten this bolt. Say this is in your kid's bunk bed and you are assembling it. And you have two wrenches, a small one and a big one. Let me just zoom out a little bit so you get the feel of scale here. On the big one, here's the small one. On the big one, the leverage is measured like so, from the exact center of rotation to the exact center of your grip, and it turns out to be 12 inches spot on. On this wrench you are exerting a force of 50 pounds. Now that's an overkill for a bolt on a bunk bed, but just go with the story. On the small wrench you have a distance of from the center of rotation to the center of your grip. That's exactly 5 inches. The question is, what force should you be exerting on the small wrench to keep the bolt from spinning? If you're exerting 50 pounds at the end of this wrench here, should there be proportionately less force exerted on the smaller wrench, as this is smaller than the big one? Or should there be more force exerted on this one? In this situation, the correct answer is more force is needed on the small one to keep it from spinning. And because the context tells you this is an inverse relationship or indirect proportion. This is an indirect proportion, okay? It is not that the smaller the wrench, the less force it needs. No, the smaller the wrench, the more force you need to apply. So let's calculate how much exactly do we need to apply. Say the 12-inch leverage is proportionate to the 5, and you can write the 5 either here or here. I'm going this way. The 12-inch is proportionate to the 5, and we have the leverage from the bigger one, so we have to write up the force from the bigger one if it is a direct relationship here. The 50 would go here, like that, if this was a direct relationship, but it is not. So 50 is coming out from there, and the 50 is going down here, and the unknown amount is going up there. And just for comparison and see what happens in a direct relationship with the same numbers, I'm going to write it up this way, and the 50 is up there. Let's calculate this one first. 12, it is 12 divided by 5 times 50. 12 divided by 5 times 50. That's a 120 pounds force to be exerted on the small wrench. And that kind of makes sense. Here is the big one, here is the small one. To keep the small one from spinning, when you exert 50 pounds of grunt on this one, you have to be hanging on for dear life and have a death grip on this one and exerting a force of 120 pounds on the small one. If you calculated with the direct proportion, which is incorrect in this particular situation, then your solution is, let me just flip both so it's easier to see. 5 divided by 12 multiplied by 50. 5 divided by 12 times 50 equals, this only gives us, we'll call it 21, it's 20.8. I'm just going to write down 21. 21 pounds of force. It's not happening that if you are cranking this one with 50 pounds of force, this one will hold up with only 21. Not happening. So that's how you can also tell if you by mistake write up your problem initially the wrong way. Take a look at the solutions here and see if they make sense. If they don't, try it the other way. So this is the correct one, and this is also good math. This is correct mathematically, but just an incorrect application for this application here. Let's look at another example from chemistry involving a calculation and molarity. Say what volume is filled by a gas, say 50 grams of how about ammonia? That NH3, that's ammonia, okay? At standard temperature and pressure. There. What volume is filled by 50 grams of ammonia at standard temperature and pressure? Now, we know that every one mole of matter or 1 mole of gas is taking up a space of 22.4 liters. Every 1 mole of matter, gaseous matter, takes up 22.4 liters exactly. It doesn't matter what it is made of. And this 1 mole of this ammonia is, they say the hydrogen is 1 plus the rest, so that's 17 grams. 1 mole of this stuff, 1 mole of this ammonia is 17 grams, and this 17 grams fills up 22.4 liters. This 22.4 liters is the amount of space that you can find in, you know, the pail that you use for putting water in for mopping. There, that mopping pail, exactly 2 of those. So that's how much 1 mole of ammonia is. And when they are filled with ammonia gas, the contents of the 2 pails for mopping is 17 grams. Now we have 50 grams of ammonia, and we want to know what volume is filled by this 50 grams of ammonia. Here is the unknown amount that needs to be calculated. And this is pretty much how we can calculate it. 17 is proportionate to 50, and the 22.5 is also proportionate to 50. This is a direct proportion. The more gas you have here, the greater volume it will fill here. It is a direct proportion. So this one is written up correctly. Small mass, small volume, big mass, big volume. Alrighty, to calculate it, let's flip it. That looks like 22.4. That looks like an obvious choice here. 50 divided by 17 times 22.4 will equal 17 equals, sorry, let's do it this way. 50 divided by 17 times 22.4 equals 65.8. 65.8 liters. Let's see if the solution makes sense. Well, 17 when 17 is doubled, it it is 34, and so this mass is more than double. It's a little more than double, maybe 2.5 times or so. So this amount must also increase at least double. So double 22 is 44, but it's more than doubling. So 65.8 kind of makes sense in its magnitude. It's important that you gauge the result of the calculation. If it if it makes sense, because if you come up with a number like 0.7, that's not gonna work. If you come up with a number like 22,874, no, I don't think so. So 65 fits the bill. That's the two examples, one from chemistry, one from physics. Keep practicing ratio and proportion until you are proficient.